Welcome back to Environmental Organic Chemistry with Dr. Lisa. We're going to finish up a very long series of lectures on hydrolysis with a kind of a short discussion of how to predict the rates of hydrolysis reactions. This is going to cast your memory back to the lecture on acid-base chemistry, which was not that long ago. And remember we talked about the Hammett constants and how you could use Hammett constants to predict pKa. Well, and so here's the equation that we used for that. The acid dissociation constant of your chemical divided by the acid dissociation constant of the reference chemical where it had hydrogens in place of the functional groups was equal to the slope, rho, which was unique to the backbone, plus the sum of the Hammett constants, the sigma values. And in a similar fashion, instead of predicting the equilibrium constants, the pKa values, we can actually predict the rate constants for hydrolysis reactions when you have these kinds of structures where you have the ester derivative here that can be hydrolyzed and it's attached to an aromatic ring which has substituents, and those substituents each have their Hammett constant. So we have the Hammett constant equation, right? So that's where we have we're predicting the rate constant of our reaction of our chemical versus the rate of the reaction of a chemical that it's not substituted, where it has hydrogens instead of the other things that might be substituted to the benzene ring. That is equal to, again, a slope term rho times the sum of the Hammett constants. So the Hammett constants haven't changed, but what we need now is we need new values of rho, and we need new values for the rate constant for the hydrolysis of these new chemicals. And so here's an example where we have some of these. We've got the rate constants for acid catalyzed reaction. Yeah, my mouse not working. So here's the rate constants for the acid catalyzed mechanism. Notice that they have no units shown, but they're, if you look down here, Ni means not important, but these are going to be acid catalyzed, and so these would be second order rate constants. Here's the rate constants for the neutral mechanism. Okay, so they would have units of a first order rate constant because the nucleophile is water, and water is assumed to be at a constant concentration that never changes, so we don't worry about it. So the K neutral has the units of a first order rate constant. Kb has the units of a second order rate constant per molar per second, because the hydroxide is involved in this. So to calculate, to turn this into a pseudo first order rate constant, you'd have to multiply by the concentration of hydroxide, which you could get from knowing the pH. So these are our rate constants, Ka, Kn, and Kb, that we could use in our Hammett constant equation. And we would get the slope terms similarly from tables like this, and we can use some of the same slope terms that we have for some of the acid-base reactions. So we can use the slope for the benzoic acid here. We could use the same slope term for benzoic acid in this reaction where we're trying to predict rate constants instead of equilibrium constants. So the Hammett equation continues to be useful, and all of those Hammett constants that we learned are still important. And then there's another way of predicting the rates of ester hydrolysis in aliphatic systems where there is no benzene ring. It's just an aliphatic carbon. The side chain is completely aliphatic. And we talked about this very briefly when we were looking at the acid-base chemistry lecture because I wanted to give you an introduction to it. And so in this Taft relationship, you figure out the rate constant of the reaction you're interested in by looking at it relative to some reference reaction. And again, we have a slope term and a sigma, which is the Taft constant for electronic effects. So this part of the equation tells you what's going on in terms of the electronic effects, electron withdrawing, electron donating ability of those substituents. And then there's also a steric component here that tells you about, there's a slope term for the steric component, and then there's an ES which relates to the substituent. Each substituent has its ES value, and they're related to basically to the size of those different substituents. So the way that you deconvolute the electronic effects here from the steric effects here is that you assume that only the steric effects matter when you're looking at acid-catalyzed hydrolysis. So you measure the rate for the acid-catalyzed reaction, you assume that this is 0, doesn't matter for acid-catalyzed, and that helps you determine the steric constants. And this works because for acid-catalyzed hydrolysis, you're assuming that everything is protonated, the leaving group has no problem leaving, and that the polar effects therefore are not as important. But for the base-catalyzed hydrolysis, both the polar and the steric effects are going to be important. So you already figured out the steric effects from the acid-catalyzed reaction, and so then you can isolate the polar effects from the base-catalyzed reaction. So the Taft relationship, again, assumes that the electronic effects are unimportant for the acid-catalyzed hydrolysis mechanism, and that's because the acid-catalyzed mechanism involves this intermediate, where everything is protonated and therefore doesn't have a charge, whereas the base-catalyzed mechanism involves this intermediate where you do have a negative charge. So those polar substituents make a big difference here because they might be helping to dissipate that negative charge or making it worse. But they don't matter over here when you're acid-catalyzed because there's no charge in the transition state. So if we look at some of the values for these sigma and ES substituent constants, for the sigma, we notice that electron donating groups, like alkyl groups here, they have negative values of their substituent constants because they're pushing electron density. Electron withdrawing groups, like bromide here, they have positive values. So, and the more here you got 3 chlorines, so this has a very large positive value. Here you only have 2 chlorines, here you only have 1 chlorine. So these have positive substituent constants because they're electron withdrawing. And then things that can resonate, like the phenyl groups and the allyl. Remember we talked about allyl carbocations and stuff. There's resonance there. They have reasonably large positive polar constants because they are able to delocalize the charge. And that makes them basically electron withdrawing. When you're delocalizing, you're withdrawing the electron density from the negatively charged intermediate. And then if we look at the steric constants, you notice that the methyl group is set by definition to have a 0 steric constant. And so the proton, because it's smaller, has a positive influence. Because it's smaller, it allows the reaction to go faster because it has less steric hindrance. And so the ES value is positive. And then the ES value increases across all these other types of groups as you get larger. So, methyl is 0, ethyl is minus 0.07. Then you get to propyl, minus 0.36. You get all the way down to a benzene ring, it's minus 2.55. So that's the largest of the groups we're looking at here. Here's another fairly large, the trichloromethyl substituent has an ES value of minus 2. So these values, they make sense in terms of the polarizability and polarity effects and the steric effects. So that's all I'm going to say about how to predict the rate constants at these reactions. And then, in the future, one of the videos I will show you some examples of actually how to do this.